Hello everyone. Welcome to another lecture of the course Digital Signal Processing. In the previous lecture, we had introduced the concept of discrete Fourier transform and we had derived the analysis and synthesis equation for the same. Now the analysis equation for DFT is given like this, and we know that here this k, which is the domain of this x of k, ranges from 0 to n minus 1, whereas this synthesis equation is given as like this, and this n also ranges from 0 to n minus 1. Now if we observe the range of this n and k, we observe that the total number of points that are available in this x of k are n, and therefore this x of k is referred as the n point DFT of x of n. So this x of k is referred as n point DFT. So now let us consider a simple example for finding this discrete Fourier transform. So the signal that we are going to consider is 1, 2, 3, 4, where this 1 is located at n equal to 0. So it can be visualized graphically like this. So we have 1 at 0, 2 at 1, 3 at 2 and 4 at 3. And now we need to find the value of x of k. So basically we need to find the n point DFT of x of n. Now what should be the value of this n? So the question that now arises is how to determine the value of n. Now basically we have three cases for choosing the value of n. So the first case is this n is equal to L, where this L is length of the signal. The second case is this n is greater than the length of the signal, that is greater than L, and the third case is this n is less than L. Now let us try to consider these cases one by one, and if we observe our example, we know that the length of this x of n, that is the value of L, is equal to 4. So for our considered example, the value of L is equal to 4. So let us go to the first case. We know that for first case n is equal to L is equal to 4. And when we discretize in the frequency domain, at that time we are going to have some kind of replication or periodicity in the respective inverse domain. So we know that we are discretizing the omega axis in n, that is 4 equal parts. So we are going to have periodic or repetitions of this x of n after 4th sample. So we represent that periodic signal, that is xp of n, as summation L running from minus infinity to infinity x of n minus 4L, where this 4 represents n, and if we visualize it graphically, it appears something like this. So this is the original x of n and this is the replicated version. So if we observe carefully, this portion here from 0 to 3 is x of n. The portion here that is from 4 to 7 is x of n minus 4, and this repeats afterwards as well as before this 0. So this discretization of omega axis, that is finding of x of k, results in periodicity, inherent periodicity in the time domain. So now let us move on and find the Fourier transform, or rather the discrete Fourier transform for this signal. And we know that for n equal to 4, this x of k is given as summation n running from 0 to n minus 1. So this factor 3 here is n minus 1, summation n running from 0 to n minus 1 x of n into e to the power minus j 2 pi k n by capital N, and we know that the value of n is 4. So this expression can be written as x of 0 into e to the power minus j 2 pi k into 0 by 4 plus x of 1 into e to the power minus j 2 pi k into 1 by 4 plus x of 2 into e to the power minus j 2 pi k into 2 by 4 plus x of 3 into e to the power minus j 2 pi k into 3 by 4. And now this can be written as this term here is raised to 0, so this is simply equal to 1, and therefore what we have is x of 0 plus x of 1 into e to the power minus j 2 pi k by 4 plus x of 2 into e to the power minus j 2 pi k into 2 by 4 plus x of 3 into e to the power minus j 2 pi k3 by 4. And we know that this x of 0 is 1 plus this x of 1 is 2, so it is 2 into e to the power minus j 2 pi k by 4 plus x of 2 is 3, so it is 3 into e to the power minus j 2 pi k into 2 by 4 plus x of 3 is 4, so it is 4 into e to the power minus j 2 pi k 3 by 4. So we have the expression something like this. So it is 1 plus 2 into e to the power minus j 2 pi k by 4 plus 3 into e to the power minus j 4 pi k by 4. So it was 2 into 2 here, so it is simply 4 by 4 plus 4 into e to the power minus j 6 pi k by 4. Now we know that the range of this k varies from 0 to n minus 1, that is 0 to 3. So we need to substitute the value of k from 0, 1, 2 and 3 in order to obtain the discrete Fourier transform. So if we substitute k as 0, then we are going to have this entire expression resulting to 1 plus 2 plus 3 plus 4, because this k equal to 0 is e to the power 0 in each and every term, so it would be 1. So we are just getting the summation of all the values, so it results as 10. Similarly, if we substitute the value of k as 1, we are left with this expression, and when we solve it, we are going to get minus 2 plus j2. Similarly, for k equal to 2, we obtain minus 2, and for k equal to 3, we obtain minus 2 minus j2. So therefore, the x of k, or the sequence for x of k that we obtain, is given as 10, which is located at k equal to 0, then minus 2 plus j2, then minus 2 and minus 2 minus j2. So this is the 4-point DFT. So this obtained sequence is 4-point DFT of x of n. Now let us consider this x of k and get back the value of this x of n using the synthesis equation. And we know that the synthesis equation is given by this formula, and let the reconstructed or the retrieved back signal be given as x hat of n. So this is given as 1 by n. So the value of n here is 4, so it is 1 by 4 summation k running from 0 to n minus 1, so it is 4 minus 1, therefore 3 x of k into e to the power j 2 pi k n by 4, which is equal to 1 by 4 summation k running from 0 to 3 x of k into e to the power j pi k n by 2. And now if we expand this, we have 1 by 4 inside the bracket, it is x of 0 into e to the power j pi 0 n by 2, so it is e to the power 0, so it is simply 1, plus x of 1 into e to the power j pi into 1 into n by 2, plus x of 2 into e to the power j pi into 2 into n by 2, plus x of 3 into e to the power j pi into 3 into n by 2. So this is the value of x hat of n, and as we have the value of capital N, the value of capital N as 4, this n also ranges from 0 to n minus 1. So this n also ranges from 0 to n minus 1, that is 0 to 3, and when we substitute the value of n from 0 to 3, the values that we obtain are x hat of 0 as 1, x hat of 1 as 2, x hat of 2 as 3, and x hat of 3 as 4. So what we need to do is we just need to substitute this x of 0 as this 10. The value of x of 1 is to be substituted as minus 2 plus j2. The value of x of 2 is to be substituted as minus 2, and the value of x of 3 is to be substituted as minus 2 minus j2, and when we do this, we are going to get back this sequence. So what we have is this x hat of n is equal to 1, 2, 3, 4, where this 1 is located at n equal to 0, and if we observe our original signal, so that is x of n, it was given as 1, 2, 3, 4, where this 1 was located at 0. So this x of n is equal to x hat of n. So what we observe here is when we have the value of n is equal to L, that is equal to length of the signal, we are properly able to find the DFT, and we are able to get back the original signal using the inverse DFT. So now let us go ahead and look at the second case where this n is greater than L. We know that the value of L was 4, so let us consider this n as 6. And we had seen that due to inherent periodicity, we have the periodic representation given as xp of n is equal to summation L running from minus infinity to infinity x of n minus 6L. So this means that this x of n, that is 1, 2, 3, 4 original signal, is going to be repeated after every 6th sample. So we have this original signal, that is 1, 2, 3, 4, and this is the periodic representation for the signal. Now if we observe here, this portion from 0, so this portion from 0 to 3 is x of n, and now we have these two zeros appended here. So this results into a 6 length signal. Similarly, we have a periodic representation here, and this goes on till infinity. So it ranges from minus infinity to infinity. So now let us try finding out the DFT for this signal. So this can be done by using the formula x of k is equal to summation n running from 0 to n minus 1. Now we know that the value of n is 6, so it would be 0 to 5 x of n into e to the power minus j 2 pi kn by 6. So this can be written as summation n running from 0 to 5 x of n into e to the power minus j 2 pi. So it is minus j pi kn by 3, and this can be expanded as x of 0 into e to the power minus j pi k into 0 by 3 plus x of 1 into e to the power minus j pi k into 1 by 3 plus x of 2 into e to the power minus j pi k into 2 by 3 plus x of 3 into e to the power minus j pi k into 3 by 3 plus x of 4 into e to the power minus j pi k into 4 by 3 plus x of 5 into e to the power minus j pi k into 5 by 3. So now if we simplify this and substitute the values of x of n, so we know that this x of 0 is 1 and this is e to the power 0, so it is simply equal to 1, so it is 1 plus the value of x of 1 is 2, so it is 2 into e to the power minus j pi k by 3 plus the value of x of 2 is 3, so it is 3 into e to the power minus j pi k into 2 by 3. The value of x of 3 is equal to 4, so it is 4 into e to the power minus j pi k, so it is 3 by 3, that is 1. The value of x of 4 is equal to 0, so this can be observed from here. So this is the x of n here. We have x of 0 as 1, x of 1 as 2, x of 2 as 3, x of 3 as 4, but after that we know that in order to make it length 6 we need to append 2 zeros, so the value of x of 4 is equal to 0 and the value of x of 5 is also equal to 0. So therefore these two terms are 0, and now if we look at this term here, that is 4 e to the power minus j pi, so this exponent, that is complex exponent, has a power that is integer multiple of pi, so this can be written as plus 4 into minus 1 to the power k. So the expression that we obtain for x of k is 1 plus 2 into e to the power minus j k by 3 plus 3 into e to the power minus j 2 pi k by 3 and plus 4 into minus 1 to the power k. And now as we had considered a 6-point DFT, the value of k will be ranging from 0 to n minus 1, that is 0 to 5. So now again we need to repeat the same process, that is substitution of the k value from 0 to 5. So when we substitute it as 0, we obtain the value as 10. Similarly, when we substitute it as 1, we obtain it as minus 3.5 minus j 4.3301. If we have it as k equal to 2, so we obtain the DFT as 2.5 plus j 0.8660. If we have k equal to 3, the value is obtained as minus 2. If we have k equal to 4, we have DFT as 2.5 minus j 0.8660, and if we have k equal to 5, the value of DFT is obtained as minus 3.5 plus j 4.330. So the sequence that we have for the DFT, the 6-point DFT, is given as x of k is equal to 10, that is located at k equal to 0, then it is minus 3.5 minus j 4.3301, then it is 2.5 plus j 0.8660, then it is minus 2, then it is 2.5 minus j 0.8660, and then it is minus 3.5 plus j 4.3301. So this is the 6-point DFT, and now let us try to find out the inverse of this sequence, which can be obtained as x hat of n is equal to 1 by 6 summation k running from 0 to n minus 1. So the value of n minus 1 is 6 minus 1, that is 5, x of k into e to the power j 2 pi k n by 6. And now when we substitute the value of n and solve this summation, what we obtain is x hat of 0 as 1, x hat of 1 as 2, x hat of 2 as 3, x hat of 3 as 4, x hat of 4 as 0, and x hat of 5 as 0. So if we write this sequence here, so we have x hat of n is equal to 1, which is located at 0, then it is 2, 3, 4, 0 and 0. And if we have the original signal, that is x of n, it is equal to 1, 2, 3, 4. So this was the original signal that was given to us, but when we need to find the 6-point DFT, we append 2 zeros to it. So if we observe these two signals here, we can see that both are equal. So we have this x of n is equal to x hat of n, which means that by considering the value of n greater than the length of the signal, we are again able to get back the original signal by taking the inverse of the corresponding DFT. So now let us consider the third case, that is when the value of n is less than L. And for that, let us consider the value of n as 2. Now as we have the value of n as 2, the periodic sequence that we obtain can be given as summation L running from minus infinity to infinity x of n minus 2L. Now let us try to visualize this signal graphically. So this is the original signal, that is 1, 2, 3, 4, starting from 0 and ending at 3. And if we have this repetitive sequence, so this blue is represented as x of n. So this blue sequence that is marked with blue color is the x of n. And if we consider this red signal, so it is x of n minus 2. So if we observe carefully, the value that are located at n equal to 2 and n equal to 3 are overlapping. And as we know that this is going to continue till infinity, and it is starting from minus infinity to infinity. So basically we are going to obtain this overlapping for all the values, which means that the original signal that we have is going to get completely distorted. So now let us see what happens to the DFT and let us see if we are able to get back the original signal. So we know that the DFT, that is x of k, so this x of k can be obtained as summation n running from 0 to n minus 1, so that is 2 minus 1 x of n into e to the power minus j 2 pi k n by n, so the value of n is 2. So this can be written as summation n running from 0 to 1 x of n into e to the power minus j 2 pi k n, so it can be written as pi k n, which is equal to x of 0 into e to the power minus j pi k into 0 plus x of 1 into e to the power minus j pi k into 1, which is equal to 1 into 1, that is 1, plus x of 1 is 2, so it is 2, and this complex exponent here can be written as minus 1 to the power k, because this factor here is basically the integer multiple of pi. And now if we observe here carefully, When we are finding the DFT of the signal, we are just considering the two values, that is x of 0 and x of 1. But the values of the signal that are present at n equal to 2 and n equal to 3 are completely ignored. So now the question arises, the DFT that we are obtaining is proper or not? So for that, let us take the inverse DFT. But before that, let us find the values that we obtain for this x of k, and we know that this k will be ranging from 0 to n minus 1, that is 0 and 1. So for k equal to 0, we obtain 1 plus 2, that is 3, and for k equal to 1, we obtain 1 minus 2, that is minus 1. So now let us try finding out the inverse DFT, and for that we know that it is given as x hat of n is equal to 1 by 2 summation k running from 0 to n minus 1, that is 1. So it is x of k into e to the power j 2 pi k n by 2, which is equal to 1 by 2 summation k running from 0 to 1 x of k into e to the power j pi k n. So when we substitute the values, we get this x hat of 0 as 1 and x hat of 1 as 2. Now this n is ranging from 0 to 1 only, means we are not going to find the value for n equal to 2 and n equal to 3, because we had considered this n as 2. Now if we observe this sequence here, that is x hat of n, so it is equal to 1, 2, where this n is at 0, where this 1 is at n equal to 0, and if we consider our original signal, so it is 1, 2, 3, 4, where this 1 is located at n equal to 0. So now if we observe these two sequences, this x hat of n is not equal to x of n. So we observe that this x hat of n is not equal to x of n, which means that we are not able to get back the original signal if we consider the value of n that is less than L. So the important observation that we are having here is we are unable to get x of n using inverse DFT if the value of n is considered less than L. Now if we are not able to get back the original signal, then there is no use of such a transformation, which means that if we want to find the DFT properly, we need to choose the value of n wisely, or in other words, or more specifically, we need to choose the value of n greater than or equal to the length of the signal. So the important observation that we have here is, in order to obtain a valid or appropriate DFT, the value of n should be at least equal to the length of the signal, or the value of n should be greater than or equal to the length of the signal. Moreover, if we observe here this condition, the value of n should be greater than or equal to the length of the signal. Now suppose the signal is of infinite duration, then how to choose the value of n? So this means that the concept of DFT has a meaning only if we are considering a finite duration signal, which means that we need to choose the value of n that is greater than L, means we cannot consider the DFT, or we cannot calculate the DFT if we have the value of this length of the signal equal to infinity, or for an infinite duration signal the DFT has no meaning. So let us summarize what we have seen in this lecture. We had started with an example of a signal, of a discrete time signal, of a finite duration discrete time signal as 1, 2, 3, 4, that is a 4-length signal, and found the DFT for 3 cases. So the first case was when n was equal to the length of the signal. So the first case was when the value of n was equal to the length of the signal. The second case was when n was greater than the length of the signal. The third case was when n was less than the length of the signal. And the main observation that we had was we were able to get back the signal when we considered the value of n greater than or equal to L, but we were unable to get back the original signal, that is x of n, if we considered the value of n that is less than L. So this DFT is moreover, we saw that this DFT is valid only for a finite duration signal, and it has no significance for any infinite duration signal. And the conclusion that we had here was the value of n should be chosen always greater than or equal to the length of the signal. So let's stop here. Thank you.